We're on 7:58 now.
Yeah. And
At
it's,
7:59, what we'll do is we'll start the live stream,
okay.
and then by 8 o'clock you should be ready to go. It usually takes about a minute to get going.
You finding more people will be watching on Facebook?
I don't know.
Yeah, typically the videos get viewed on Facebook.
The problem I've heard is that it's harder for them to ask questions because it's just streaming.
Yeah, there won't be questions coming in from Facebook. I won't be watching that.
Because I've gone to some webinars, and what they say is if you're on Facebook, go to Twitter, and they give you a hashtag to send a question to.
We're not sophisticated yet.
Yeah, almost. We're close. All right, it's 7:59, Mary. I'm going to start the live stream.
I can't talk. I'm on my webinar.
All right.
Okay.
Yeah, and Al, I'd kindly ask that you shut your phone off.
Yeah, it's off. I'm going to put it in a different room. And I'm going to take care of it so I don't... I'm going to go up into my menu and turn off any notifications.
Hold on. Okay. All right, it's going live. Preparing live stream.
Al, share your screen. Al,
What?
did he share his screen?
Okay, want me to share screen? Okay, 1 second.
All right, I'll need the title of the talk.
Yes. What is a white dwarf?
All right.
Okay. Tell me when I should start, or are you going to make announcements first?
I'll make an announcement.
Okay.
George will, then I will, then you will, George. Then you start.
Okay.
Okay. Capital W, capital D.
Yes.
Going live. Okay. I think we're live.
Good evening, everyone. Welcome again to Amateur Astronomers Incorporated for our Fridays at Home presentations. AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford, New Jersey. Since the observatory is closed at this time, we're holding our weekly presentations online. Tonight's speaker is Dr. Al Gottlieb, who has been a member of AAI for about 10 years now. He received his PhD in experimental solid-state physics from Brandeis University, and he worked at Bell Labs for over 25 years. He's taught at Clark University in Worcester, Massachusetts, at Seton Hall, NJIT, Union County College, and King University. So the title of his presentation this evening is What is a White Dwarf? So go ahead, Al.
Okay, and thank you all for attending. And we're going to try to be a little interactive in the beginning. 1 second. Why is my slides not running? 1 minute. There we go. So before we begin, I'm going to ask you to be involved by sending your response to via either your chat or questions and answers. And that is, how many kinds of dwarfs are there in astronomy? Snow White had 7 dwarfs. And actually, once had a student, when we were talking about that, gave that as an answer. She wrote down, the 7 dwarfs, which I don't remember, Snoopy, whatever. But how many dwarfs are there in astronomy? And so I would like to take a minute to have you send in your response to any white dwarfs you can name, any dwarfs that you can name in astronomy, and don't include the white dwarfs. Is there any other dwarfs that you know about? And are there 7?
All right, everyone, if you could post your answers in the chat box, I will read them out to Al.
Yeah.
Okay, we've got some answers coming in.
Okay, great.
We've got Lonnie Bunis posts FGKMRNS7 question mark. Wayne Petco posts the sun.
Okay, anybody else?
Alan has posted, I just bought white dwarf sunflowers.
But that's astronomy white dwarfs, though. We need astronomy.
Okay, so Cliff has posted red, brown, and yellow.
Okay.
Dennis Conti has posted brown dwarfs.
Okay.
And this is all that's come in.
Okay, so let me go and look. So we have white dwarfs, which we'll talk about today, which are stars. They're the end of the star's life. They're the remains of a star that's slowly dying. There are brown dwarfs that someone mentioned, and they're wannabe stars. They're massive objects that are more massive than a planet, but not big enough that gravity could squeeze them. We'll talk about them to be able to become a star. There are very small stars. The smallest stars are red dwarfs. And then we have black dwarfs, which are white dwarfs that have slowly cooled so that we can't see them anymore and they become black. And there are dwarf planets. That was a newie since they demoted Pluto, and Pluto now is dwarf star. And we found very small galaxies, and we call them dwarf galaxies. So unlike Snow White, who has 7 dwarfs, in astronomy, we only have 6, unless someone finds something else. So the discovery in the year 1783, 2 years after discovering the planet Uranus, British astronomer William Herschel, probably with his sister, Caroline, became the first person to see a white dwarf star. He didn't realize that it was anything different than a star that he saw in the sky. And on the evening of January 31st, Herschel observed through his telescope a second object that was a faint star surrounding. He saw a binary star around 40 Erie b, which was a very faint object, and it happens to be a white dwarf. And we'll talk about what is a white dwarf. And at the time, he didn't recognize it being anything unusual. It was just a star, okay? So what are white dwarfs? The strangeness of Herschel's star did not become apparent until another 127 years. And in 1910s, using spectroscopy, and I'll mention again about Steve Lowe and his talk on June 10th, talked about him doing a spectroscopy, looking at breaking the colors of light from an object and getting information on that object other than just observing what it looks like, revealed that 40 Erie b and 2 other stars had surfaces temperatures that were much hotter than the surface temperature of our sun. But they were so close to the Earth that if they were normal stars at that temperature, they should be visible with the naked eye, and yet they weren't. So the only conclusion was that these objects had to be very small, and we'll talk about these new objects. And from the size being so faint, they had to be extremely small, about the size of Earth, or about 1/100th the diameter of our sun. Okay, so these are strange objects. And the white hot surfaces and small diameters provided a name for this new class of stars, white dwarfs. So they're small, very small stars, but their color being so hot it gives off white light, and that's how they were named. And so white dwarfs, So white dwarf was again first discovered by William Herschel and Caroline Herschel in 1783. It was in a triple star system, 40 Erdani. The brightest star is always given the label A, and the B star in this triple star sequence was a white dwarf star. And the brightest star in nighttime sky being Cirrus, the dog star. And Cirrus is actually a binary star system with its companion, Cirrus B, is a white dwarf star, and it's one of the nearest white dwarfs to us. It's only 8.6 light years away, just right up the block. And here is an artist's rendition of how bright Cirrus A is, and its companion, that little dot on the right side, which is the white dwarf Cirrus B. Just like to make a comment that if there are any questions, please send them in. I like participation, and so I will check with George every once in a while to find out if there's any questions while I'm talking, so you don't have to save them to the end, and we can talk about that. So white dwarf stars, which are the ones circled in this picture, are in the globular cluster M4, and the brightest stars in this field are yellow stars, similar to our sun. Smaller dim stars are red dwarfs, and the really dim stars are white dwarf stars, but their temperatures, surface temperatures, extremely hot. So any class of stars, of faint stars representing the endpoints of the evolution of what we call intermediate and low mass stars will end their days as a white dwarf star. So a white dwarf is a star, but it's the end of the star's life. The star had effectively is dying by this amber. If you've ever been at a campfire, and when the fire is almost out, you have these very bright ambers, and they are very bright, but they slowly cool and lose their light producing capability as they cool, because there's no mechanism for them to make energy to make light. And that's what a white dwarf star is. It is just a very hot amber of the inside of the sun, the core of a star that is over 100,000 degrees, that is slowly cooling. And we're seeing it as it slowly cools, which takes billions of years, but it's a cooling object. And we're seeing it because it's just so hot, it's giving off radiation. And so-called white in color because when they first discovered them, they were very hot objects. So they were even hotter than bluish stars. And so they looked white. But when they looked at how big they were very small. They happen to be, which is interesting, and we'll talk about this, their mass, the mass of these stars are roughly the order of our sun, one solar mass, but yet they're the size of the Earth. And we'll talk about how dense these objects are. And because of their large mass and small diameter, such stars are as dense and compact objects with an average density of 1 million times the density of water. And 1 gram of water, 1 cubic millimeter of water, centimeter, 1 cubic centimeter of water weighs about 1 gram. And this would be 1 million times as dense as water. And you wonder how this can exist. So I'd like to talk about how a star dies. I'll do it rather briefly. I apologize, but I just like to go over just how a star dies and why most stars end up as being just this white dwarf star. So when a star reaches the end of its long days, they run out of fuel, and they go through a sequence. And what remains is the amber of its core, the inside of the star, this glowing, very hot amber that slowly cools. And this is the dying remains of a star. The ancient stars are incredibly dense. By the way, a tablespoon of matter from a white dwarf star would weigh as much as an elephant, 5.5 tons. So imagine a tablespoon. I don't know many tablespoons can hold that kind of mass, but its weight is 5.5 tons. And so a typical white dwarf star has the radius of about 1/100th the size of our sun, but the mass of the sun. So it is extremely dense object. We have nothing like this that exists on Earth. Stars like our sun fuse hydrogen in their core, making helium. And white dwarfs are stars that have burned up all the hydrogen they've used as nuclear fuel, and the star then dies. And we'll give a model of how that happens. Fusion in a star's core produces heat, and when a gas gets hot, it wants to expand, but the competing force is gravity. And so there's an equilibrium in a star, in its core, in its furnace, as in your furnace of your house, if you have a house, is generating heat, and the star wants to expand, but because of gravity, it squeezes it, and there's a happy equilibrium. And the star, for most of its life then, is producing energy. We see it as light by converting hydrogen into helium. But what happens is when the hydrogen used as fuel vanishes and fusion slows, gravity causes the star to collapse on itself. And the ultimate force is gravity. And so here is a quickie model of what could happen in the life and death of a star. Okay, this will be on your test. You'll, in 1,000 words, describe this. And what it is we call a star that is a star by definition is producing energy in its core, in its furnace, by converting hydrogen into helium. By the way, we have done this in an uncontrolled way, and that's called the hydrogen bomb, which produces a phenomenal amount of energy, 1,000 times more energy per mass compared to splitting the atom as an atomic bomb. And a big push that's happening outside of Geneva is, can we do this in a controlled way? And if we can, we could make almost an unlimited supply of energy on this planet and not have to burn fossil fuels. What governs what a star is going to do is what its mass is. So your birth mass, if you're a star, tells you what you're going to be in life, how bright you're going to be, how long you're going to live. We're more complex than a star, maybe. If you know your birth mass, I can't tell you much about what's going to happen about you. But with a star, I can tell you everything. And for a medium-sized mass star, which are 98% of stars are low mass and medium mass, they'll end up as going through a sequence of first converting hydrogen to helium, main sequence. When they run out of fuel, they become a red giant. And then when they run out of fuel completely, they become a planetary nebula. I'll talk a little more about those. And inside the very center of that planetary nebula is this glowing amber of the core of the star, and that is a white dwarf star. And as that star cools, and eventually we will not be able to see it because it'll be so dim, we call it a black dwarf. So we have now gotten 2 of the dwarf stars, okay? By the way, if you're a very high mass star, you end as a supernova, and you can become a pulsar or a black hole, okay? A neutron star or a black hole. That's for another day. So dwarf stars are 98% of all stars will end up as a dwarf star. Okay, only 2% of stars which have masses greater than 8 times the mass of the sun end their life as a supernova. And so far, white dwarf and black dwarfs, red dwarfs, by the way, as shown in the next slide, are very low mass stars. There are stars that are fusing hydrogen into helium in their core, but they are very low mass stars. And so they're very small stars, but they produce light. And so they're the red dwarfs. And then the last piece is something called brown dwarfs. And they're sort of wannabe stars. There's not enough mass that gravity can squeeze them so that their core temperatures can get high enough to have fusion taking place, and they can convert hydrogen to helium. So they're wannabe stars, okay? And so we've gotten the 4 types of stars now: brown dwarfs that are not really stars, red dwarfs, white dwarfs, and black dwarfs, and then of course the dwarf planets and dwarf galaxies. So to complete the model, here is this on what will happen to a star by its mass. The very low mass stars will, between 0.08 and 0.4 masses of the sun, are red dwarf stars. They're very low mass stars, and they just will be living for a rather long time, hundreds of billions of years. Matter of fact, every red dwarf star that has been made since the birth of the universe, 14 billion years ago, thereabouts, 13 and a half, are still around. If the mass of a star is less than 0.08 masses of the sun, that's the brown dwarfs. And then it goes up and shows you that if the mass is between 0.4 and 8, it'll end as a white dwarf. Okay, and that's what we'll talk a little bit more about today. By the way, when in the 1910s, when they realized that these very dense objects were white dwarf stars, at that time, astronomy said every star is going to end as a white dwarf star. We now know that that's not the case, that there are very massive stars that will become supernovae and end their days not as a white dwarf, but strange objects, either a neutron star or the most strange object in the universe, a black hole. So the key to our understanding, and that's what was nice about Steve's talk, because on June 10th, is that us amateurs, can actually do spectroscopy on stars because it tells us everything. So that was Steve's talk on June 12th. And so spectroscopy, which breaks up the light of the star into its particular colors, provides information on both the chemical makeup of the surface of an object and also the temperature of the surface of that object by using spectroscopy, okay? It allowed the women of Harvard Observatory to classify stars by particular characteristics of the spectroscopy that they observed. And they made tremendous breakthroughs in our understanding of different types of stars dependent on the star's surface temperature, okay? Good for another talk. I love to talk about that because those women just contribute so much to what our understanding of stars are. By the way, not only does spectroscopy tell us what the surface composition is in terms of its chemical properties, the temperature of the surface, but it actually could tell us if the object is moving towards us or away from us. So white dwarfs was a mass of the sun combined to the volume of the Earth. We have no capability of doing this on Earth. That's how dense it was. So I'd like to take a quick break and from George. Have there been any questions at this point? Otherwise, I will continue.
Yes, Al, there is one.
Good, great.
It's from Isbel.
Okay.
And to his credit, right before we started to move on, he posted that dwarf planets is one of the dwarfs that we have.
Great.
But
okay.
his question is, for many years, I had read that stellar black holes were formed by the gravitational collapse of supermassive stars with mass so large that they could not become supernova. For some years now, I have seen that it is suggested that black holes are also formed by supernova. So was the theory of non-explosion gravitational collapse discarded?
Well, if you saw the picture I showed a couple slides back, if a star has a mass of greater than 25 solar masses, 25 masses of the sun, then when it runs out of fuel, it will become a supernova, and the remnants of the supernova the star itself will collapse and become a black hole. And so that is one way that we make black holes from the death of a star, typically greater than 25 solar masses, up to, there's been stars now that of 100 solar masses that they didn't think could exist, but seem to exist for a period of time, and again will become a black hole. So that seems to be what we observe. The observation of black holes that we did with the Leica experiments with the looking for gravitational waves, that were black holes that were combining when two galaxies combine, each one having a black hole, and eventually the two black holes of the two galaxies will combine to form one larger black hole. And when that happens, a tremendous fracture of the gravitational field is generated, a pulse, and that is what we pick up on this planet. But when a black hole forms, we can observe it if we can catch it. But a dying star of super high mass, better than 25 solar masses, will eventually become a black hole, as far as we know now. So how could such an object support itself against its own gravity? So you have an object 1,000,000 times as dense as the density of water. Okay, so the question is, how could that happen? What process could make such a star? And today we have some of the answers to these. Okay, so we'll talk a little bit about it. I will not do it complete justice, but we'll talk about it. So during a star's lifetime, there are two forces fighting for its on itself. The first is the inward force of gravity, as I mentioned, and the other is the pressure of the heat of the gas of the star from the temperature pushing out. And so this star reaches a point of equilibrium where the force of gravity and the force of thermal expansion are in equilibrium, and the star continues as long as possible. Opposing gravity is the outward force of the graph pressure, as I mentioned, provided by the high temperature inside the star, and that is generated by nuclear fusion initially, and for most of the star's life, converting hydrogen into helium from the lowest mass to the next lowest mass element. Although energy is lost by radiation, the star remains high temperature through nuclear fusion as it burns hydrogen into helium. And these two forces balance each other precisely, creating a stable cell structure, at least for a while. By the way, one of the things to appreciate is that stars do have a finite life. They don't live forever. And the discouraging is, by the way, the more massive you are as a star, the shorter your life, but the brighter you are. So eventually, the star's central reserve of hydrogen exhausted, your gas tank runs out of fuel, your car stops unless you can get to a gas station and refill. Most stars don't have a source of refilling, and so they exhaust their hydrogen. And fusion ceases at the center, but continues a little bit on the surrounding outside the inside core. That causes the outside of the star to swell and the inside of the star to compress and shrink down. And within the core, the inward forces of gravity starts to squeeze and the star collapses. And the gravitational energy released by the core combined with the energy output of the burning shell puffs the outer shell. And so the outside of the star blows up to become a red giant, typically 1,000 times this diameter of the star, the size of the sun. Okay, and when this will happen with our sun, in about 4-5 billion years from now, it will engulf most of the planets inside, including us. And so we should have had left before then, but we should be okay for a while. Some of the outer envelope breaks free and cools, and this is what we call a planetary nebula. Now, I find this hard, but it says, because early astronomers confused these structures with planet look like Uranus. Why they left the name as Planetary Nebula, why couldn't they change it? I don't know. But anyway, so a planetary nebula, and I'll show you some pictures at the end of the talk, are not anything to do with planets. They're the remains of a star that is dying because it's falling apart. And finally, glowing proudly at the center of the nebula is the collapsed core, and that is our burning amber, that white dwarf star. And this is a model I got from one of the papers I read. It says, to understand the magnitude of how the collapse is, how dramatic it is, go to a bowling alley. I guess we can't do that now, social distancing, and find the heaviest bowling ball they have. Okay, then take it in your hands and squeeze it. I don't know if you can do this, but try until it becomes the size of this letter O. Okay, so squeeze that ball down to this little letter O, and compressing that much mass in such a small volume creates a very dense vowel. And this is the same degree of compression a white dwarf faces during its final gravitational collapse. It doesn't collapse down to nothing, but it gets rather small. So being the size of the sun, it collapses by a factor of 100 to the size of the Earth. Okay, but the forces of matter inside the star, the electrons, and keep the star at this size. And so there's not enough force of gravity to collapse down more, but it has done a lot of damage already by reducing the size by 100. So what's the inside made of? The central regions of a typical white dwarf star are composed of carbon and oxygen. Okay, matter of fact, as the star cools, it will crystallize, and so it will be crystalline carbon. Does anyone know another name for crystalline carbon? If you put that in the chat box, we'll come back to that. Okay, and surrounding this core is a thin envelope of helium in most cases, and an even thinner layer of hydrogen. Okay, so a few white dwarf stars are surrounded by a thin carbon envelope, and the reason we know this again is that we get the characteristics of the surface of the star by using the spectrum of light that we observe. Okay, and only the outermost stellar layers are accessible to our observation. So like even now, when we look at the sun, we only see the outside surface of the sun. We don't know what's inside directly. There are other ways to model what's inside the sun or inside a white dwarf star. And so there are flavors of white stars. This will not chocolate, vanilla, and strawberry, but they're DA, DB, DO, and PG 1159 stars. And those are dependent on what's on the surface of the stars. If it has mainly hydrogen on the surface of this white dwarf star, it is a DA. If the surface of what remains of the star is helium, then it's a DB. Nearly pure ionized helium, they call it DO. And if it has only exposed hydrogen and oxygen, it's the PG 1159. And that depends on how the star dies. And so this is what our spectroscopy has picked up on this. Okay. The next few slides are planetary nebulas. And note that in the center, the bright object is the white dwarf star. That's the main burning amber. And except for the last picture, all were taken with the Hubble telescope. Before I proceed, did anyone answer what is another name for carbon that is crystallized?
Yes, Al, we've had several answers.
Okay.
From Nancy Twaskis, Brian Lemley, Stephen Cosma, and Isbell all answered diamond.
Fantastic. And so the Beatles song, Lucy in the Sky with Diamonds, probably we're seeing white dwarf stars that have cooled and crystallized.
And Al,
Okay.
we do have one question in the queue too,
Sure.
if you'd like.
Sure, please.
This is from Neil Yablonsky.
Okay.
Probably a few slides back.
Okay.
Does a black hole evolve in something else?
As far as we know, No. However, Stephen Hawking had a model in which he said that slowly things could happen where a black hole could evaporate and eventually not become a black hole. However, the time that this takes place is hundreds of billions of years, even for a small black hole. And so it hasn't been verified, his model of a black hole evaporating. But at this point, once the black hole forms, it is there. By the way, we don't know what is a black hole because we don't have the physics to deal with what it is. The problem is that in nature, we either have the laws of quantum electrodynamics, which explains very small matter as long as gravity is not important. And then we have the model of gravity, which is general relativity. But the two cannot be put together to come to a uniform model to explain something that's microscopically small that has a lot of gravity. So we really don't know what a black hole is. Matter of fact, it's just one of these strange things. And it was predicted, by the way, in a few years after Einstein published general relativity. The first main paper was 1915. During the World War I, Schwarzschild, who unfortunately didn't make it through the war, he was in the trenches, came up and modeled that a black hole could exist. But what it is, we don't know. All we know is matter has been compressed so much by gravity that its size is infinitely small in what it looks like. So let me go over some of the pictures. By the way, you can still have more questions. So here is a planetary nebula. This is in the globular cluster M15. It's the gas of the star, the outer layers of the star has expanded so much that it's almost transparent, and you're seeing stars through the this object, the planetary nebula. And in the very center, the central star is that burning amber, the white dwarf. Another picture of a planetary nebula is NGC 7027. Notice, by the way, the shape of this planetary nebula. Effectively, every planetary nebula seems to be different, like a butterfly. Every butterfly looks differently, but what you see though in the center, the central star, that's your white dwarf. That will be the remains. The planetary nebula, the gases will slowly expand and cool, and in 15,000 years, what will be seen will be this glowing amber of the remains of the star. By the way, so far all these pictures were taken with Hubble. NGC 6827, another white dwarf star in the center of this beautiful planetary nebula. Here's another one, Mazel 3, which is 3,000 light years from Earth. Look at this one. It's gorgeous. I mean, you see these two arms coming out from the center of this planetary nebula, and it's beautiful glowing gases that we see. Here's the butterfly nebula. Again, it's the remains of a star that its outer envelope has expanded away from the central core of the star, and in the very center is the white dwarf star that remains. And the last one is from someone in our club, Isabel Gonzalez. She had sent this around to everybody, and I go, "Ooh, you got the Helix Nebula, and this is a planetary nebula." She did a great job of getting this off of the telescope system, and in the very center of this object, in that very center, is that white dwarf star, and this is the remains of that star that's slowly dying. And so thank you for coming. And as I always end, clear skies and may the force be with you. Okay. And any additional questions, I'll be happy to answer. And I'll stay around for as long as we want to do afterwards to talk about this. There's a lot of stuff in this. White dwarfs fascinating me because it shows the end of life of a star. It also shows how our thinking went from thinking that every star died this way to finding out that some stars, very few, end as either a neutron star, which is a strange entity. We can have a whole lecture on that. And some stars end as this really weird thing called a black hole, which people again said, oh, it's in the mathematics, but this stuff will never exist. Well, surprise.
Al, there is no more questions, but there is one comment from Dennis Conti.
Okay.
He says, it might be worth mentioning the role of white dwarfs in type 1A supernova.
Ah, okay. By the way, thank you. There's so much to talk about with white dwarf stars, but I'll mention it. Okay, thank you for raising it. And that is when a white dwarf star is in a binary star system. By the way, over 50% of all stars we find are not by themselves, but are in either two or more stars going around each other. And we know they go around each other because we watch them and we can see that they're going around each other. They're not just hanging in space close together. So if a white dwarf star is in a binary star system and its mate happens to become a red giant or even a super red giant, so the white dwarf star has died already. Its mate hasn't died yet, but is becoming, at its very end, though, a supernova as a red giant. It gets so big that some of the mass of that star is brought to this white dwarf star. It gets it, it creates it, and it increases its mass. So it gets more massive. Which means that gravity gets stronger and can squeeze it even smaller. And if it gets enough mass, gravity can squeeze it so that now it collapses to become typically a black hole and explodes as a supernova. So we have actually two classes of supernovae. One class is a star just at end of his days being more than 8 times as mass of the sun. When it ends its days, it explodes, but it's a shockwave explosion. The star blows out as a shockwave, and then what remains is either a neutron star or collapses to nothing as a black hole. And that's typically a type 2 supernova. Type 1A is a white dwarf that gets so much mass that gravity squeezes it and it blows up as actually as a carbon bomb. The carbon in the white dwarf, because remember the white dwarf is mostly carbon and oxygen, gets so hot that it's a thermonuclear reaction of carbon and it explodes. And the reason these are so important is that the size that this happens is roughly the same. And so that the amount of energy given off by an explosion of a white dwarf star in a binary star system typically is roughly the same size. They're all roughly the same size, a little variation, but roughly the same size. And so the amount of light intensity that you see on that explosion are similar in size. And so they make a phenomenal, what we call a standard candle, an object of known brightness, where when a star that is high mass dies, it could be anything 8, 10, 20, 19.2 solar masses. And so the amount of light that it gives off is very variable. And so it doesn't make a good standard candle. But so these are very important. And that's what was used to find that we believe that the universe expansion is accelerating and that the universe is expanding faster than we thought. maybe. Okay, thanks for that, mentioning that. But that's a talk in itself. So there's a lot of stuff here, but thank you.
Okay,
Hope I answered the question.
Yep. Yes, we have one more question from Stephen.
Okay.
Just a comment. One of the highlights of John Adams, second president of the United States, work in Europe was meeting William Herschel, already a superstar.
By the way, one of the things I like to credit, which normally isn't given, his assistant, who was really with him all the time, was Carolyn Herschel. That's his sister. And I really credit her as being there with him. She would take the notes as he did the observation. Remember, they didn't have film at the time. And so she would take his notes. By the way, she was a comet finder in her own right. But I really feel that she was there when he observed Uranus, and also when he observed this interesting looking star. And she was there. She deserves credit for a lot of this stuff. But he was a superstar. What I find interesting, he was of German origins and came to England as a musicologist, but his hobby was building large telescopes. And he, by the way, wanted to name Uranus as George. By the way, this is the same George that this country had some issues with in 1776. So the Herschels proposed that this new planet would be called George. And the International Astronomical Union said, no, we don't name planets after people, but mythology figures. And so I guess maybe to get even, they picked the name Uranus or Uranus. Okay.
All right. Yeah, there are no more questions. There are no more comments. With that, I'm going to end the live stream.
Okay.
Thank you, everyone. Clear skies. Oh, go ahead, Barry.
Okay.
Just to mention, thank you everyone for coming. Thank you, Al. And next week, our presenter will be Dr. Mary Lou West, and also an AAI member. And she will speak of the life of a star, probably even more in depth than what we had tonight, too, about the lives of stars. Thank you.
Okay, great.